Hey there, today we're going to be talking about antiviral medications, okay? So let's get right into it. There's only 4 different types of antiviral medications that are commonly used. Just so you know, antiviral medications, it's tougher to make it work than, say, like antibacterials, because the thing is that viruses kind of hide out inside of cells, so they're a little bit more adept at getting around the system. Also, the thing is that they're not like alive in the traditional sense like other cells, right? They're kind of like on the borderline between life and maybe just being like a poison. So the thing is that you can't really interrupt the life cycle. You can't really interrupt the respiration. You have to find other ways to get rid of them. So let's talk about it, okay? The first one we're going to talk about is something called Neuraminidase, okay? Neuraminidase, okay? Now, what does neuraminidase do? Okay, now, there's actually a couple type of something called sialic acid, okay? And that's going to be on the outside of the host cell and on the on the viron, or the virus, right? Viron means like a free-floating virus inside your body, okay? And it's going to catalyze hydrolysis of the terminal sialic acid. And what this is going to do is it's going to promote motility of the virus through the respiratory tract. So the viruses that we're thinking about, probably the ones like influenza, the ones that are you cough on someone and they get sick. Okay. Also, what it's going to do is it's going to prevent budding of the cell. Okay. The cell's it's gonna cause problems. The cells it can't really bud and spawn off the other viruses, right? So what's gonna happen is the cells kind of get stuck. Can't really eject those viruses. So here's a little memory tip that I use to help out, right? The thing is, let's take a look at what's going on here. Here we see a virus-looking thing, right? Icosahedral shaped type of thing here. Usually the virus has like these legs coming out, but in this case, it doesn't really have that. It kind of just has this long thing coming out. The same thing for this cell over here, kind of like a host cell. Just so you know, host cells are actually usually much larger than viruses, actually always much larger than the viruses. So this is not really to scale, but it's just there to help you visualize some of the tools that I've used to try to help you memorize what's going on here. So we could see that both of these guys, right? They have, doesn't this look kind of like a neuron? You have like a little cell body, you have an axon here, right? And then you have like a little dendrites, this type of thing again, right? It's like a neuron, right? Neurons, neuraminidase. Look at this right here, these blue arms, right? They kind of look like what? Like N's, like nitrogen, right? So that would be like aminos, right? Neuraminidase. Okay, you could remember that. I also see something funny going on. Look at this. There's like these light bulb heads, right? They look like aliens, and they're kind of like shooting, right? Little purple beams out of their head, right? That's because they have psionic powers, okay? And that's supposed to mean that they are using a sialic acid, right? They have sialic acid, and the thing is that, look at this, right? You see this blue line coming across their necks, it's chopping, right? It's chopping it off. The neuraminidase chops off the sialic acid through hydrolysis. So you can see like there's like a little water drop at the end of this particular line, right? The water's cutting off the psionics or the sialic acid, okay? Another thing that happens is that neuraminidase, what it'll do is, okay, look at these little red lines, right? They're zapping each other, and then you see like on the top, it may be hard to see, but there's like a little bit of a, let me draw it in right now, okay? There's actually a bump here going on, right? And actually you could think about like these whole things, right? They're kind of like big bumps actually coming out of the cell themselves. Actually, the more important one is point to this one over here, right? And that means that it prevents budding, right? It prevents budding of the cell to keep the reproduced viruses from escaping. So it kind of interrupts the reproductive cycle of this particular, the infected cell, right? That is infiltrated by the virus. Another thing to remember is that you see the little arrows right here, right? Coming into the thing, right? What does that look like? That's like where the lungs would be, right? That's to help show that it actually promotes mobility through the respiratory tract, right? You see that? Yeah. So I hope this picture is going to help you remember. I know it's going to help me remember. Those neuraminidase, right? Not the easiest thing to remember about viruses. Let's get to the second guy over here, right? These are called M2 protein inhibitors. Uh-oh, M2, I've never heard of that in my life. Well, actually I have, and I'm going to explain it to you, okay? But I didn't hear about it until like a day ago. But now I know what M2 protein inhibitors do, okay? M2 protein inhibitors, well, if there's an M2, there's got to be M1, right? So what are these guys doing? Let's take a look over here, okay? I've drawn this little picture over here. And, okay, I know it looks like a cell. Is it a cell? No, it's not a cell, okay? It's actually a virus, right? The icosahedral shape again, right? And, you know, these little legs hanging off, I guess you could call it, right? And this in here, right? Look at this. This is going to be like the RNA material that's stored inside of the head, okay? And M1 is actually going to be linking, right? Holding that RNA to the capsule head, okay? And M2 is going to be the channel right here that actually allows hydrogen ions to go inside. So you can see some other things going on here, and you probably know what that's all about. It's probably me trying to draw some stuff to try to help me remember exactly what's going on here. So let's get into it, okay? So now, the first thing to remember is that M2, right, protein inhibitors, guess what? It has to do with M2 right here, right? I did draw a guy near M1 and M2, but both of these drugs, right, okay, are going to be affecting M2, okay? What's the class of this particular drugs, okay? Well, okay, we have some superheroes over here, okay, and this guy has a big A on his shirt, right, okay? That's because, okay, his secret identity is actually known as Adam, right? So we use Adam to remember that it's a adamantane, okay, adamantanes, right? That's the class of the drugs right here. Now let's take another look, right? What does Adam become? A man. Okay, look at that big A in his chest. He's a man, yeah. And that stands for mantase, right? Oh, whoa, don't want to mess that up, right? I would say mantase, but don't forget this little plate he's holding, right? That means it's time for him to dine, eat out somewhere, right? A man to dine. Look at this guy over here, right? What's that supposed to be on his chest right there? Well, the yellow markers don't work so well. It's supposed to be rye on his shirt, right? Rye. Rymantadine, right? He's rye man, right? Rymantadine, right? Rye man to dine, right? To dine, right? Over there, right? Now, how do these things work? Okay, now, the thing is that, remember we said it's an M2 blocker, right? And what is M2 actually doing? What M2 do is, right, what the M2 channel does is, it allows acids to build up inside of this little capsule here. What that's going to do is it's going to cleave the M1 protein cord right there and allow it to go free into the cell and start doing its dirty work, you know, taking over the machinery of the cell. So, take a look right here, right? Rymantadine, right, is spitting acid onto this little chain that's holding a man's arms together, and it's freeing him, right? Look at the acid dripping down, right? Okay, that's to help us remember what M2 and M1 do. Make sense? Sure does, okay? So I think that's a pretty good way to help me remember exactly what's going on with this particular guy over here. Okay, let's move on. Wait, is there anything else? Yeah, I explained everything, right? Yeah, okay. Let's go to the third class over here. Antiretrovirals, okay? And I guess one thing that we really talk about is, we have 1, 2, 3, 4, 5. Actually, there's 5 classes, right? Okay, come on. Did I say 4? I'm in 5. 5. Okay. So antiretrovirals, what they do is, okay, we have either, right? My mistake. Okay, there's only 4. It's 4. 4 retroviral classes, okay? Now, the thing is that the reverse transcriptase inhibitor, we're going to talk about that more in depth, and this is actually an example of that. Actually, scratch that. Okay, scratch that. We're going to rewind back to this point, okay? Let's talk about the third class over here, which is going to be called reverse transcriptase inhibitors. Okay? So the thing that what I want to remember about reverse transcriptase inhibitors is going to be RNA, DNA, RNA, right? Reverse transcriptase. I got RNA inside. Can I go and start just doing my stuff immediately, you know, making proteins? There are some viruses that do that. This isn't one of those cases, okay? Actually, what happens to RNA creates DNA, which creates RNA again, and then you start to have your business going on, right? One of the reasons why I wanted this is because there's a magic number 3, 1, 2, 3, and there's 3 things, right? First of all, there's 3 different classes of these reverse transcriptase inhibitors, and 3 kind of plays another part because on the third, right? On the third, well, let me see, give me a second. Okay, ribose, right? RNA, and DNA too, right? It kind of looks like this, right? And then you have some things hanging off here, right? But on this guy over here, right, there might be an OH here, right? Okay. Now what happens is that for this guy, right, these analogs, okay, you have a nucleoside analog or a nucleotide analog, right? You just considered 1, 2, 3, right? Okay? 1, 2, 3. And this guy over here, right, something happened to this guy, right? They changed the OH for an N or something else, right? Something else is going on here that's not allowing the molecule to really act correctly and is preventing the further continuing transcription, translation, or even replication of DNA. And this is going to cause the cell to stop producing, stop reproducing, and to basically just stop its life cycle. It's going to die, right? Shut it off the DNA, right? It's not good for it, okay? So on the third piece right here, right, the hydroxyl group, something's going to happen to it. Also, sometimes this this molecule needs to be triple. You have to add 3 phosphates to it, right? You got to supercharge that molecule, right, in order to make it active. So, you know, that's known as 3 times phosphorylation. So remember 1, 2, 3, because the third hydroxyl group is 3 times the phosphorylation. Also, okay, there's also the idea of, what is it? OPPP, right? Okay. OPPP, right? Yeah. OPP is actually a famous song by Naughty by Nature. I like rap music, so maybe a little catchy tune can help you to remember the 3, right? Nucleoside, nucleotide, and non-competitive inhibitors of RT, right? There's 3 members of Naughty by Nature. What is it? Tretch, Vinny, and DJ. Oh man, I don't even remember. How could I not remember the DJ? Oh well, I guess it happens. Anyways, let's get back to the business over here. So, okay. When we talk about NNR, well, actually, let's go back to these ones, the nucleoside analogs and the nucleotide analogs, okay? Now, this is med school, so some things here are going to be a little bit annoying to memorize, and this is one of them, okay? Nucleoside, RTS is for nucleoside, right, reverse transcriptase inhibitor. It would make sense if we said nucleoside reverse transcriptase inhibitor NSRTI, nucleotide analog reverse transcriptase inhibitor NTRTI. Nope, it's actually, we don't talk about this S right here, okay? It's NRTI for this one up here and NTRTI. Yeah, why make it NSRTI? Why make it, you know, easy and make sense? Let's just make another layer for you to remember. Well, there's a little trick here, okay? Nucleotides have an extra piece on the molecule, okay? Nucleosides are missing that piece. So you can remember that nucleotides, you need a little extra, you need that extra T in there, okay? Hope that's helpful. Once again, the non-competitive inhibitors of reverse transcriptase. Remember, when you have a non-competitive inhibitor, that means it does not bind the active site, okay? If it does not bind the active site, then that means that, you know, there's certain things that happen within the physiology, right? And as in terms of competitive inhibitors, about how you can actually overload, right? Let's suppose that we have a competitive inhibitor, right? Then if I load a whole bunch of the competitive inhibitor inside to the system, right? I can actually reverse that by putting in a whole bunch of the normal product in there, right? And then it will actually displace the competitive inhibitor. But non-competitive inhibitors, right? It occupies some place besides the active site. So even if I load a whole bunch of the substrate on there, right? it's not going to actually make a difference. This is a concept from physiology, okay, and like sometimes talking about CAMs, which is the opposite of affinity. Just a little way to remind ourselves and go back and play with some of the concepts from earlier in med school. Okay, you're probably taking immunology after taking physiology. But if not, hey, this is a little step ahead, right? Why not? Okay, let's move on, okay? So, you know what? Actually, let me talk about the example here, okay? So in this case, you see that I have different colors here. Isn't that so exciting? Because we're going to talk about something that's you may have heard of, something called AIDS, okay? And AIDS is actually an example of a reverse transcriptase inhibitor, of a drug that we use reverse transcriptase inhibitor for. But, okay, do we use just reverse transcriptase inhibitor? No, actually, if you remember, people who are having AIDS, we give them a whole bunch of different antiviral medications. And another one of those is going to be something called integrase. Okay, let's look at a little bit of the mechanism of how these particular guys work together, because they do work together. Okay, the first step is HIV enters CD4 plus, right? What is CD4 plus? That's talking about the T helper cells. Okay, and the T helper cells, there's there's cytotoxic T cells and there's T helper cells, right? What's the difference between these two categories of T cells? Well, the thing is that the T helper cells, what they do is they kind of like prime the B cells to make antibodies. So what happens is that by the AIDS virus, by destroying the CD4 T helper cells, they're actually compromising part of your immune system, okay? The adaptive part, right? Not the innate part. Anyways, okay, let's move on, okay? The second step is the viral RNA turns into the DNA, and you can actually start to interrupt what's going on there with the reverse transcriptase, right? We talked about that, right? The thing is that, just so you know too, an example of a nucleoside or tide, right? Let's say it's nucleotide, right? Nucleotide analog would be a drug known as AZT, okay? And that's actually an analog for thymine, right? Thymine, right? ATCG, right? So adenine is pairing with thymine, right? And if we take a look at the pairing of adenine and thymine, the thing is that, okay, cancer cells and virally invaded cells, their mechanism for correcting errors in the DNA code are usually offline, okay? Because honestly, they've been compromised, right? And they actually don't want those mechanisms to work because they will inhibit their progression. So you can usually use actually antiviral drugs are often also used for anti-cancer drugs. Okay, that's just something to keep in mind. Okay, and this is no exception. Okay, these actually no, there's some of these things they actually use more exclusively with AIDS though. Okay, some I guess for some nucleotides are better to attack than others for certain reasons, right? Like ATP is used for energy. GTP is also used in the purine pathway to regulate the whole cycle. So there's different things going on, okay? Like with the, they all have their own like individual role, and the way that AZT works in the system just may be more effective than hitting another nucleotide. So after we have the reverse transcriptase, right, we're going to have another step that happens after that, okay? And the integrase binds the viral DNA and exposes OH groups, right? That's going to be hydroxyl groups. And what is that going to do? Let's think about it, right? There's something called methylation of DNA. So if you remember back to organic chemistry, there's this thing called a methyl group. Where can I put it? Let me put it over here. Okay. A methyl group is like this, okay? And a methyl group isn't really very polar. So it's pretty non-reactive, right? Okay, this is kind of like if we wrap that around the DNA, it's going to down-regulate the activity of that DNA, or the expression of whatever that DNA creates. But if we have an OH over there, right, that's going to make it more active, right? Okay, this is kind of polar, right? Look at that lone pair over there, right? Ready to engage in some kind of action, right? So over here, let's take a look. Integrase will expose the OH groups, it's going to enter the nucleus, and then it will bind the host and the viral DNA, and then all the bad stuff happens, right? It starts taking over the host's DNA, and then it starts to make the cells start making more viruses, eventually killing the cell, and that's how viruses work. Okay, so remember, right? Integrase versus transcriptase, not exactly the same thing, but they have some kind of relationship right there. Okay, let's get to our last guy over here, acyclic guanosine inhibitor. Oh my goodness. Now, the thing is that I've worked in some healthcare facilities, right? Some private practices, some hospitals, things like that. And one of the, someone comes in and, oh my goodness, wow, that person's kind of attractive, right? Could be a guy, could be a girl, right? Like, oh wow, this person, they look like they could be on TV or on movies or something. Then you go into the chart, not going to say any names, but oh my goodness, they're taking acyclovir. And you're like, because that means that they have herpes, and that's kind of sad. So, you see quite a lot. I guess the temptation's high. When you look good, you have other good people around, and I know I would be super tempted if I was better looking. So, yeah, it's sad. You're like, oh wow, that person looks kind of good. Then you're like, oh wow. For the second time, it's not as good, right? So, acyclovir, right? And it's activated by viral thymidine kinase. What does that mean? Okay, that means that, I don't have herpes, and let's suppose I inject myself with acyclovir. Will that acyclovir start to act on my cells? Nope, and this is why. Because the thing is that it's activated by a viral thymidine kinase, right? Unless it's invaded by the virus and starts to make this thymidine kinase, right? Which is actually going to add a phosphate to this particular molecule, right? This is not made normally by our cells. It's only made after viral infection. So this drug over here is actually, you could call it a prodrug, right? It doesn't really work until it's activated by this particular thing, which is only present after viral infection. Okay, but how can we remember this? Okay, besides remembering acyclic guanosine, right? And just the word acyclovir, you're like, oh my goodness. For me, just they say that when you memorize things that are more ugly, actually, they say that people who are ugly are actually more memorable. But it's just there's quite an incongruence there to see someone who's attractive and you're like, oh wow. Then you look at their cycle and you're like, oh wow. That's so I just always remember acyclovir just for that reason. Let's take a look over here. Okay, we have a cycle over here. We have a guy over here, right? We have the guy, and he's got his little leg here, right? That's a male symbol. We have a female over here, and there's a female symbol over here, right? She's holding that, okay? And we see that the cycle of herpes is getting passed around. How unfortunate. And, how are we going to remember the word thymidine kinase, okay? Well, take a look at their thighs right here, right? Their thighs actually, or their leg is made up of the symbol for male and female, right? Thymidine, right? Now the thing is that I added a little extra symbol in here, right? It's kind of easy to remember something like that, right? And it's like sexually transmitted. So you see this thing going on here, and you can see that this kind of looks like a K, right? A K shape, right? You see that? So thymidine kinase. Okay, I hope that's thymidine kinase. Okay, why she got something sticking up, who knows? Just use it to memorize it, right? Thymidine kinase. These are the 4 types of, maybe you could say this is the 5th one, right? These are the 4 to 5 different types of antiviral medications. It's helpful for me. I hope it was helpful for you. Thanks for checking us out. All right, that's it. Thanks for checking out SGU TV. Please make sure to like, comment, and subscribe, and check out our other videos.